So listen. So today we are going to discuss the last part of fluid mechanics, which is called as surface tension. Okay. So let's see. You would have heard this word, right? Surface tension. Yes or no?
Yes, sir.
So here, tension refers to some force. Surface means the outer layer, right? So here we are going to discuss about surface tension, and this concept is something which is related to fluids. Okay. So before we actually get into the concept of surface tension, we need to know certain forces which are called as cohesive force and adhesive forces. Okay. So let me explain what that means. So cohesive forces means if at all you are able to talk about the force of attraction, okay. See, with respect to both cohesive and adhesive, in both the scenarios, it means force of attraction only. But the question is about the force of attraction between what kind of particles? Okay. So that's what the question is. So if the force of attraction is existing between the molecules of the same substance, okay, then those forces are called as cohesive forces. Okay, it is because of this cohesive force only what is happening is we talk about a definite shape that solids have. See, generally when you talk about a solid, okay, let's say you have a wooden box in your hand, wooden piece in your hand. So it is made up of many particles, right? Right. So if the force of attraction is existing between the particles of the same substance, then that kind of a force is called as cohesive force. Means what we are trying to say is the solid is able to exist in the shape of what we are able to see only because of the force called as cohesive force. Guys, am I clear with this?
Yes, sir.
Yes. So that's what happens. Now the next question is about what do we mean by adhesive force? See, for example, I give you a paper. Okay. I'm asking you to stick it to the wall. What are you going to do? I give you a notice, okay. Let's say I'm giving you a notice. I'm saying you go and stick it in the notice board. You attach it, that's a permanent notice. Just stick it to the notice board. What are you going to do? You'll use some glue, right? You'll apply the glue. You'll apply the glue to the paper. You're going to go and attach it to the notice board, right? So the paper is able to exist in the shape of a paper due to what? Due to the cohesive force within the paper molecules. But here what do we have? You have a wall. Wall is a different substance, and the paper which we have in our hand is a different substance. How are you able to create a force of attraction between these two? I'm saying attraction because they both are sticking together. So how are you able to, what is actually creating a force of attraction between the paper and the wall? It is the adhesive force. Okay. In simple terms, sometimes what you can see is you go and buy a glue or something, right? You can see this word on top of it. For example, Fevicol and all, they use the word adhesive because it is used to attach two different substances. So adhesive force is nothing but the force of attraction which is existing between the molecules of two different substances. Okay, I gave you an example which you can see, but see, for example, I take a chalk piece, okay, visualize it, I can't show it now. I take a chalk piece and I write it on the board. So if I say you have a green board in your school, right? So green board before I use the chalk is completely green in color. But as soon as I place a chalk piece, I start writing on it. What exactly is happening to it? Some particles of the chalk, aren't they going and getting deposited on the green board according to the pattern in which I write? Guys, are you able to understand?
Yes,
Right.
sir.
That is why if you see the size of the chalk piece will not remain the same. You're losing its size, no? Why is it happening? Because some particles of the chalk piece are lost and they're getting stuck to the green board. You're able to write because of friction, but the way the process where the particles of the chalk piece get stuck to the green board is called as adhesion. And the reason for it is, adhesion is a process, and the reason for it is adhesive force. In a similar way, when you write on a paper, the ink from your pen is getting stuck to the paper while you write. That is also happening because of the adhesion. Ink is a liquid, paper is a solid. It's happening. Okay. Why this word is very important is because we will be able to observe the concept of surface tension only when one object comes in contact with a liquid. Okay, that is the reason why I'm stressing on this force. So if you're clear, I'll proceed. Okay, I'll just read out one last statement. When you pour water in a container, let's say you have a glass container. Okay, you pour water in a glass container. Okay, and from the glass container, let's say I have a glass here. When you try to empty this glass container, will you be able to find some droplets of water on it?
Yes, sir.
Yes. So here, tell me, what are all the forces that are acting? The force between the water and the glass is
Adhesive force.
Adhesive force.
whereas the force that is existing between the water molecules is cohesive force. In this
Cohesive.
scenario, yes, right, you're able to visualize it. So when you talk about a glass, when the beaker is completely emptied, will you be able to find some amount of wetness?
Yes, sir.
Yes, sir.
Yes. So that is when you're trying to. So I'm talking about the substance here. That is water, guys. Water and a glass. I'm not talking about any other beaker. I'm very particular here. Water is the material I'm using, and it is taken in a container which is made up of glass. When you pour it, you will be able to find it because the reason for it is. See, this might be. See, if I have to speak in terms of marks, this might be a 1-mark question. But practically, what exactly is happening is the force of adhesion, because the water molecules are getting stuck to the glass, the force of adhesion between the water and the glass is greater than the force of cohesion between the water molecules. Now you can ask a question, do I have any material in my hand where instead of water, if in the glass container I use that material and if I try to empty it, I will not find any wetness in it. Do you think there is a material like that existing? Are you able to understand? So I have a glass beaker or whatever it is. So instead of water, can I think of some other material where when I try to empty it from the beaker, I will not be able to find any wetness in it? And the answer,
Solid, sir.
we can think of mercury. Yes, solid is one of such examples. But I'm talking about a liquid. Okay? Because I'm talking about wetness. No?
Yes, sir.
So, on the contrary, I'm extremely sorry. 1 minute. So, on the contrary, what will happen is you take mercury instead of water. If you try to pour the mercury from the beaker into some other beaker, you can find absolutely no wetness in it. And what is the reason for it? It is purely happening because the force of cohesion, that is the force that is existing between the mercury molecules, is greater than the force that is going to exist between the mercury and the glass container. Are you guys able to link both?
Yes, sir.
Yes,
Right.
sir.
This is a very, very important point, guys. This is going to help us to understand surface tension. Okay, because we'll be seeing some concept called as capillarity. Sorry, capillary action. They're all simple concepts. Don't worry. Only technical names are slightly confusing. We'll try to understand what is the concept. So, shall I proceed?
Yes,
Somebody
sir.
remind me after the class. I will send you this document so that you need not write and waste your time. Okay. Now I'm going to the next concept, that is molecular range. So here comes an important question. See, when we learned Newton's law of gravitation, what does Newton's law of gravitation state? When there are two particles separated by distance r, then there exists what? Then there exists a force of attraction. Gravitational force is always attractive force, such that it is directly proportional to m1 into m2 and it is inversely proportional to the distance square, where distance is the distance of separation between those two particles. Am I right? Now comes an
Yes.
important question. When I have two masses m1 and m2, if I keep increasing the distance of separation between them, okay, I'm repeating it. If I keep increasing, that is, I move m1 to the left and m2 to the right. If I keep doing this process, will I be able to still find the force of attraction when I try to separate them to the maximum possible distance also? Do you think it will still exist? Look at it mathematically, as the value of R is going to increase, because F and R are inversely proportional. As the value of R is increasing, will the force not decrease in proportion to it?
Yes,
When
sir.
that,
Yes,
when that is going to happen, will I be able to achieve a state where the force of attraction is going to be zero? When will I be able to say that the force of attraction between the particles is zero? That is when R is at infinity. Am I right?
Yes, sir.
So this R is equal to infinity. I will call it as the range, because I need to know what is the distance of separation I need to bring between these two particles so that my force of attraction becomes zero. So can I call it as a range? In a similar concept, what is going to happen is, since we are speaking about the adhesive force and the cohesive force, both are related to what? Both are forces of attraction which are existing between molecules. Then we need to define a certain distance of separation between those particular molecules till which the force of attraction is going to exist, and that particular distance of separation is what is called as molecular range. Right? Range is generally maximum value. So range existing, the maximum distance existing between whom? Between the molecules of a substance. So let's see what does a molecular range mean. It is the maximum distance up to which a molecule can exert some appreciable force of attraction, or of attraction, not repulsion, I'm sorry, which can exert some appreciable force of attraction on other molecules. It is of the order of 10 power minus 9 meter in solids and liquids. So what I'm trying to say here is, okay, if I have water, then if I take a particular water molecule, let's say I have water filled up to height h. So in this height h, I can find many water molecules, right? So in those many water molecules, if I take only one particular water molecule, let's say this one, then I'm able to find one water molecule here, one close to it, right? So this water molecule, which I will call it as the source. I'm just using a technical name, source, because this is the one which is trying to attract. My interest of study is about this molecule. What exactly is the molecular range this particle possesses? So there are certain particles which are close to it, and there are certain water molecules away from it. So in the vicinity which is close, I can find many such particles like this which are at the same distance. Similarly, the particles which are away from it, I can find at the same distance. Are you guys able to understand these 2 points? Now, I'm saying the source is able to attract this particle. Beyond this, it is not able to attract the particles which are next to it. So then what can I call this distance R as? So try to understand the source particle. You have a particle here. Between these two particles, you can have many particles in between and many particles on the right. Okay, I will place it like this. This is the source. This is the target I'm trying to talk about. Okay, so the target particle is here, means from point A to B, if I take any molecule, any water molecule, then the source is able to attract that water molecule. And the maximum distance from A till which it is able to attract the particle is B. Beyond this, even if there is any particle, it will not be able to attract. Then what can I call this distance AB as?
Molecular range, sir.
That's what is called as molecular range. Means within that distance, you place any particle close to it, it will be able to attract. Beyond that, it will not. Okay, now read the definition, you will understand. It is a maximum distance up to which a molecule, that is a source molecule which I spoke, can exert some appreciable force of attraction on other molecules. Other molecules are the target molecules. Okay. Generally, if you try to measure this distance, it is approximately in terms of 10 power minus 9 meter, which is 1 nanometer, which is a very, very, very small value. Okay. So this is what is going to exist in the case of solids and liquids. Shall I proceed?
Yes,
Yes,
sir.
sir.
Now comes an important point. So you have learned what are circles, right? So how do you define a circle? If from a fixed point, right? If from a fixed point you are able to find many points which are at the same distance from that fixed point, then when you join all those points which are at the fixed distance, what shape are you going to get? So if I join
Circle.
all, so if I join all these things, I'm going to get a circle, right? So when I'm talking about molecular range, try to understand, guys. This is A, this is B. Okay, this is B is the maximum point beyond which it will not attract. Within that, yes, it will be able to attract any particle. Means if I have a particle here, if you ask me a question, will the particle at A be able to attract? The answer is yes. Any particle that is lying within B will get attracted. Beyond that, it will not. So when that is the molecular range, now comes an important question. Is circle a two-dimensional shape or a three-dimensional shape? So what is the equation of circle? X square plus y. I hope they have started this in your school, right? X square plus y square is equal to a square. So
Yes,
how many
sir.
variables? How many variables are there?
2 variables, sir.
So two variables means it's two-dimensional, right? So circle is a two-dimensional shape. Now comes the question. All these particles that I'm trying to talk about are water molecules. Will water molecules be present in two dimension or three dimension?
3 dimensions, sir.
It's a three-dimensional shape. So when a circle is extrapolated to a three dimension, what shape does it generate?
Spherical, sir.
It's a sphere. That's right. Be confident. It's a sphere. Why I'm using the word sphere is because, can I say this particle at A, if I take, see, I cannot draw a sphere here, but visualize it. If I take any particle which is in B need not be only in the plane. It can be towards me. It can be away from me. So you're going to have a sphere. So within the sphere, if I take any particle, will A be able to attract or not? So in that spherical shape, inside if I take any molecule, will it be able to attract or not?
It will be able to, sir.
Yes,
It
sir.
will be, because it is within the molecular range. So what is the radius of the sphere? The radius of the sphere is literally nothing but the molecular range, right? So if you are able to define something, see, sphere of influence doesn't exist. That's how we define actually. Okay, I'm trying to say this is the region within which I'm able to sense the molecular attraction existing. Okay, so what is the sphere of influence? It is a sphere drawn around a molecule as center, that is A as a center, with a radius equal to the molecular range is called as the sphere of influence of the molecule. So the molecule at the center attracts all the molecules lying within the sphere of influence. Does it make sense?
Yes, sir. Makes
Right. So this is about sphere of influence. Okay. So from here, we are slowly going to develop the concept of surface tension. But before that, let's see. So while studying the behavior of a molecule under the influence of cohesive forces, we need to consider only the molecules lying in the sphere of influence. So this is an important point. So if you're trying to study about the cohesive forces existing between the molecules, cohesive means existing between the same molecules, you need to speak about only those molecules which are lying within a region called as the sphere of influence. Okay. So what are all the terms that we have seen? We have seen what is the cohesive force, adhesive force, molecular range, sphere of influence. So these are some basic terms. The next concept that we are going to see is a surface field. Okay. So surface means the topmost point, right? When I say surface of Earth, what am I trying to say? It's the outer layer, right? I can say the outer boundary. So a thin film of liquid near its surface having a thickness equal to the molecular range for the liquid is called as a surface film. Have this in your mind. Okay. So a thin film of liquid near its surface having thickness equal to the molecular range is called as a surface film. Means what I'm trying to say is the best example for this is you have a soap water, right? So when you talk about soap water, you will be able to see small bubbles and all those things, right? On the surface, you'll be able to see some bubbles and all those things. Especially, you would have seen this, right? When you put some detergent in your bucket, or let's say, have you seen this when they try to mop the floor, they put some detergent, and when they switch on the tap, when the water falls, there will be small bubbles that will be coming up.
Yes, sir.
Yes,
Yes, sir.
you would have observed that, right? So when I talk about the surface, near the surface on a microscopic level, there will be a very thin layer of that liquid. That layer that is existing, look at the thickness of it. What is the thickness? It's of the molecular range, means 1 nanometer. So on that surface, you will be able to see a thin film, which is given a technical name called as surface film. It's a molecular concept, molecule level concept, means it's a microscopic aspect. Okay, so that I cannot explain beyond that, but have this point in your mind. Right? Am I clear till this point?
Yes, sir.
Yes, sir.
Yeah. Now we will see what exactly surface tension means. Okay, let me read out this point. When you talk about a steel needle, okay, a steel needle, when I talk about a steel is generally going to be, so when I talk about a steel needle and water, tell me which is going to be more dense. Is steel more dense than water or the vice versa? If I
Steel
talk
is more
about,
dense than water.
obviously steel is more denser. So what does Archimedes principle state? When you have a denser material, when a denser object comes in contact with a uh, less denser object, when more denser object comes in contact with a less denser object, what is going to happen? The one which is having more density, will it
Will
float
sink.
or sink? It is
Thanks,
going to,
sir.
it should sink, right? That's what Archimedes principles told. But here, look at this point, no? When I talk about a steel needle, you can make it float on water. Steel needle having more density, but you're able to make it float on water. How? That's the question, right? True. So though the steel is more dense than water, and the question is, why is it happening? How is it able to? How are we able to achieve it? It is because of a property of that liquid called as surface tension. So I've taken some images for you guys to understand. Okay. See, this is the one which they are trying to speak about. Are you able to see this? So you have a pin, right? A clip, whatever it is. So this clip is able to float on the surface of water. It is actually not going into the water, though it is more dense. Why is it happening? Because the liquid is able to exert a force which is able to balance it. When is something going to dominate, right? Now, the question is very simple. Physics tells us that throughout physics we understood one concept. An object is going to move, or it is going to, an object's motion will be dominated provided the force applied by it is going to be more compared to the opposing one. That's what the whole physics says. So the pin is going to exert a force in the downward direction. Water will try to exert a force in the upward direction. And important point, don't get confused of this with the buoyant force. There's not buoyant force. Because for buoyant force to come into existence, what is needed? When can you speak about the buoyant force? Sorry? Recollect the statement of Archimedes principle. Now, what is what is the statement with which Archimedes principle starts with? When an object, when you talk about an object, it's a solid. When a solid is dash or dash, Immersed in a liquid.
Fully or partially immersed in the
Yes.
water.
When we use the word completely or partially, means at least some portion of the solid has to get immersed into the water. Whereas when I talk about a pin, I cannot define its volume, which is going to be very, very thin. Okay, the reason why I'm stressing on this point is I told you during Archimedes principle that whenever a solid and a liquid come into picture, come in contact with each other, we need to think in terms of Archimedes principle. Here also you have a solid and a liquid, but the difference is here the solid is restricted to the surface. There, the solid is getting immersed into the liquid. That is the difference. Am I clear with this? I hope you'll not make any mistake in the future.
But sir,
Am I
even
clear?
if we immerse, it will again come back up, right, sir?
That will come, but see, but what does buoyant force state? It is the density of the liquid into volume of immersed portion into G. This is what mathematical expression. So for
Yes,
me to define buoyant force, I need some portion of the volume to be immersed. Are you able to understand?
okay, sir.
Means, so if I have a cube, if I immerse a cube, that cube should get completely gone into the liquid. Not completely, at least partially. I'm sorry. It's not completely. It's not like the cube is going to be on the surface and so if suppose the cube is on the surface itself, if it is like this, then what is the reason for it to get balanced? So scenario 1 and scenario 2. In scenario 1, who's balancing the weight? Weight is common in both the cases. In scenario 1, what property of the liquid is actually balancing the solid?
Buoyant force, sir.
In this case, it is buoyant force. Buoyant force. Whereas in the second case, what is happening? The solid is not even able to cross the surface.
This is due to surface tension, sir.
That's right. Now you're able to understand the difference when to think of what.
Yes, sir.
Right? So that's what I'm trying to stress upon because there's a confusing point. Solid is coming means you start thinking in terms of buoyant force. Don't do that. So here the pin is getting balanced because of the buoyant force. So if you're able to see from this side, there is something that is going to happen. I'll tell you what will happen. Similarly, you're able to see a mosquito here, the second diagram. I think there is a clearer one. So you're able to see a mosquito, right? So when the mosquito is trying to walk on the water, are you able to observe what is happening to the surface of the liquid, wherever the mosquito is, whatever it is coming in contact with the water?
Yes, sir.
Yes,
You're able
sir.
to see the remaining part of the liquid. So remaining part of the liquid, if it is horizontal, what has actually happened at the places where the mosquito has come in contact with the liquid?
The water molecules there have been displaced.
Yes, they are displaced in which direction?
In downwards direction.
They are displaced in the downward direction, right? But still, the water is not giving up. It is able to balance this mosquito. It's not like it has given up and the mosquito is getting drowned. No, it will still be able to walk on surface. Okay. For example, the mosquito is able to walk on the surface of water because of the property of liquid called as surface tension. Okay. Similarly, you observe this diagram. No, there's more precise. There also, you're able to see, no, wherever the object has come in contact, it does get displaced. So when I see it from the side view, right, will it not look something like this? There's a surface of water. So the molecules on the surface of water, what has happened is, initially, if you see the water surface to be horizontal, when the mosquito comes and sits on top of it, what is happening is, there is a small curvature that is not getting designed. Are you able to understand? So initially, when the mosquito was not there, when you see from the side angle, you can see that the surface is horizontal. Whereas when the mosquito comes and sits, what is happening? You're able to see a small curvature. Right? So when can this kind of a curvature exist? Only when that material has elastic properties associated with it. So it should have some elastic property because as soon as the mosquito goes away, the water will be able to come back to its original shape. So is it not like this water surface? I'm talking only about the surface because the topic itself is surface tension. My interest of study is only about the surface. I'm not concerned about what is happening inside. So on the surface, I'm able to say that the liquid is behaving like an elastic membrane, due to which it is able to balance whom? Balance the mosquito. Right? So that elastic property, technically the elastic property that is exhibited is what is called as surface tension. Let's read the definition. See. It is so now we will see what is surface tension. It is the property by virtue of which the free surface of the liquid. Please make an important point here. Free surface means the surface which is exposed to air molecules. Okay. So write it down. In this chapter, free surface means the boundary that is exposed to the air molecules. If I take this as the boundary, for example, if I take this as a boundary, so on the top of the boundary you have air, below that what you have? You have liquid. So how many free surfaces does it possess?
Could you repeat?
Saying you have liquid. See, for example, I will take this diagram itself. So you have the water in the beaker. This is the surface, right? So you have air here and you have liquid here, right? So surface is the boundary I'm trying to talk about. Air is above medium, liquid is below medium. Now, how many free surfaces does water have? I told you free surface means what? The surface which is exposed to air. So how many free surfaces? It has only one. Similarly,
One.
if I talk about a water drop, generally it will be in this shape, but it can be approximated to a sphere. If I talk about a water drop, how many free surfaces does it have? So for a water drop, inside what is present? Inside it is completely
liquid.
It is completely water. Yes, it is liquid. So this is the surface. So this surface is separating what media? It's separating
Water and air.
liquid and air. Now, how many free surfaces does this have?
Once.
One, sir.
One. So you would have seen a soap bubble, right? You would have seen a soap bubble.
Yes, sir.
Yes, sir.
You have those colors and all existing. So when you talk about a soap bubble, what is present inside? Inside, do you have liquid or is it hollow?
Hollow, sir.
So inside you will have air. Outside also you will have air. So how many free surfaces does a soap bubble have?
Two, sir.
Yes. So have this point in your mind because we'll be using this. Are you guys clear with the word free surface?
Yes, sir.
Yes, sir.
Yeah. So now we
So
can
I have a
proceed.
doubt. How much
Yeah, tell me.
free surface you told was there for that soap bubble, sir?
It is 2 because surface is this. I'm using black color. See, this is the boundary is the surface. So on the left of the boundary you have air. On the right of the boundary you have air. So that surface is getting exposed to air on both the sides.
Okay,
So
sir, understood.
It has 2 free surfaces. Yes. So why I'm stressing is, see, now the definition uses the word free surface. You need to understand what it is. So what is it? It is the property of whom, that is the property of the liquid, by virtue of which what is going to happen? The free surface of the liquid at rest behaves like an elastic stretched membrane tending to contract so as to occupy the minimum surface area. Okay, why it is minimum surface area and all, I'll explain, don't worry about it. Tell me 2 things. In the surface tension concept, are you clear with what is free surface? I hope you're clear with it. There are 2
Yes, sir.
important words. Free surface,
Yes,
and
sir.
they're using the word at rest. For example, the mosquito is at rest only because it is getting balanced. So when the mosquito was sitting, what did I say? It will start getting bent. So it will start behaving like an elastic membrane. So by behaving so, what exactly it is doing is, it is tending to contract, right? Elastic membrane. So when I say elastic membrane, it can either get contracted or expanded. But for surface tension, what is happening? Is it getting contracted or expanded?
It's contracting, sir.
It's contracted. So what is the difference? Is contracted means the particles coming close to each other. So when I talk about these particles at the surface, when it is getting contracted, what will happen is these particles will tend to come close to each other. So here surface tension is happening only due to the contraction. Okay. By getting contracted, what exactly is happening is it is able to occupy minimum surface area. That's what the concept is. Okay. Shall I proceed?
Yes, sir.
Yeah. So now see, you can, as shown in the figure, let's now we are going to derive the mathematical expression for what exactly is surface tension. Okay, listen. So you can imagine a line AB on the free surface of a liquid. So you know what is a free surface by now. So on the free surface of a liquid, the small elements of the surface on this line are in equilibrium because they are acted upon by equal and opposite forces. This also I told you. When an object is getting stopped on the surface itself, if there is an equal and opposite forces acting and the object is getting balanced, the reason for that is the surface tension of that liquid. So the question comes is, listen, the small elements of the surface of this line are in equilibrium because they are acted upon by equal and opposite forces acting perpendicular to the line from either side. So one force is up, one force is down. Okay. So the force acting on this line is proportional to the length of the line. You can imagine like this. So what I'm trying to say is, you have a pin of this size, right? I gave you a pin of this size. But tell me one thing, is every pin in this world made of only this size?
No,
No,
sir.
sir.
Obviously no, right? So depending on the requirement, we will be changing. So this pin has a length L associated with it. Similarly, if I drop a smaller pin, then maybe the force that is needed to stop this will be less, right? If I call it as L dash. So what I'm trying to say here is, read the statement. That line AB on the free surface, you can imagine the pin. The small elements on the surface of this line are in equilibrium because they are acted upon by equal and opposite forces acting perpendicular to the line from each side. So the force that is acting on this pin is observed to be directly proportional to length of it. Okay. The force that is going to act on the spin is directly proportional to length. So when I remove the proportionality symbol, the constant that we introduce is capital T, or some books write it as sigma. Okay, T into L, where this T is what is called as surface tension. Okay, so the surface tension of a given material is a constant. Okay, so write it down, guys.
So I have a doubt.
Yeah, tell me.
So you told surface tension is a constant, no, sir. So does
Yeah.
that mean it will be every type of liquid will have the same value, whether it be oil, water?
Yeah, that they should have the same value. It is a property of that liquid. So the property of the liquid is going to be constant.
Okay, sir.
Yeah. So the surface tension is given as the force per unit length. So this is the mathematical formula. Please remember this because all our derivations are based on this concept. So what will be the SI unit, all those things you will think. If you're clear with this, I'll proceed to the next part.
Clear, sir.
Yes,
Okay.
sir.
Now it is. So till now we saw how to derive that value. Now we will see how it is measured. It is measured as the force acting per unit length on an imaginary line drawn on the liquid surface. So the direction of force being perpendicular to this line and tangential to the surface. Okay. So that is how you measure the surface tension. So what are the units of it? Force per unit length means Newton per meter. CGS unit is dyne per centimeter. Dimensions will be dimensions of force by dimensions of length. It is mt minus 2. Okay.
Yes, sir.
Yeah. Now comes the next topic, that is we will be explaining surface tension on the basis of molecular theory. So what exactly, how the molecules at the surface behave, how the molecules inside behave, and all those things we are going to see. So molecular theory of surface tension. So in the diagram 10.44, that is, we take PQRS is the surface film of the liquid. I told you what is the surface film, right? There will be a thin layer of film on the surface of the water whose thickness is how much? Approximately 10 power minus 9 meter. But this 10 power minus 9 we can't see. This is only for diagrammatic purpose. This is a highly zoomed version. Okay. So consider the molecule A. So we are considering three molecules. I've taken one molecule A, which is completely inside the liquid, one molecule B, which is in between the film, and one molecule C, which is exactly on the top of the surface, exactly on the surface. Am I clear, guys?
Yes, sir.
Okay. So consider the molecule A well inside the liquid. So what will happen is, if I take any molecule here on the sphere of influence, this molecule A is equally attracted in all the sides. So this molecule A, can I say it is going to be at equilibrium? Because it is experiencing equal force in all the directions. As simple as that. Now, what can I say about B? If I talk about B, observe what I'm going to do. So the particle here, okay. So I'm taking one particle on the surface, another part. I'm taking three particles. All these three particles will create a force like this, right? The other particle will create a force in the downward direction. Tell me one thing. So here, what I'm trying to say is the size of the arrow will decide the magnitude of the force. Okay. Now tell me, in this case, whether the force it is experiencing in the upward direction is more or downward direction.
Downwards.
Downward direction.
Downwards.
Downward is more because the arrow mark is more, as I told you, right? Now see what is going to happen when the downward force is more. What should actually happen to that particle? The particle is going to should actually start experiencing, or I can say the particle should actually go in the downward direction, right? So see what is going to happen. Now consider molecule B lying inside the surface film. Its sphere of influence lies partially outside. So sphere of influence is partially outside. But what has happened here is this part is empty. There is no water molecule here. Nothing is going to happen. Okay. So this molecule experiences less force upward and more force downward by the molecules in its sphere of influence. Similarly, when you take molecule C, what is going to happen? It is completely going to experience a force in the downward direction because above this there is no liquid. If there is no liquid, I cannot speak about cohesive forces. If I cannot speak about cohesive forces, I cannot speak about molecular range. If I cannot speak about molecular range, there is no sphere of influence. So for the particle at C, the sphere of influence is existing only within the liquid. Are you guys able to visualize all the three? For A, the sphere of influence is completely inside the liquid. For B, some part is outside the liquid. Whereas for C, it is completely inside the liquid. Only you are able to see only a hemisphere. You're able to see only half a sphere of influence. Right? So half its sphere of influence lies above the surface. The resultant downward force on such molecule is maximum. So due to this downward force, what will happen is the potential energy of the molecules of the surface film is higher than those lying inside the liquid. Okay. So whenever the adhesive force that is going to act, so where is the force more? Force is more in the case of C followed by B. But both are existing within what? They are close to the surface. Right? Because this is inside the surface film, this is exactly on the surface. Right? So with this, what is the important point we can speak about is the potential energy of the molecules of the surface film. So if I talk about the molecules of the surface film, is definitely higher than those lying completely inside the liquid. Okay. So for a system to be stable, this is a very, very important point. Now tell me one thing. I have a ball here. I have a ball here. I'm not holding both. Which one will be stable?
The one underground.
The one on the floor. And the reason for it is very simple because can I say it has least amount of potential energy?
Sir.
So the ball on the floor is having least amount of potential energy, whereas the one at the top has more amount of potential energy. So try to have this point in your mind. It is not related only to this ball example. Try to remember throughout physics or throughout science, energy plays an important role. So whichever is having more energy will be more unstable. So for a system to be stable, potential energy must be minimum. I cannot say, I will not say zero, it should be minimum. Okay. So for the surface film to have minimum energy, the number of molecules in it must be minimum. Thus, the surface film tends to have minimum surface area. As a result, the free surface of the liquid at the rest behaves like an elastic stretch membrane. That is the reason why here we are trying to say it will try to occupy minimum surface area. Are you able to understand? Am I clear, guys? Is
So
there
can
any
you
doubt
repeat once more, sir? The last
from where?
part.
Last part. Okay. So this point are you clear? For a system to be stable, potential energy should be minimum. Is that point clear with that
Yes,
ball
sir.
example?
Yes, sir.
Okay.
Yes, sir.
So what we are able to understand from the whole theory that we discussed is, I'll ask you some basic questions. You answer that, you'll get your answer. 1 minute. Now tell me these questions. 1 minute. See, I have three molecules. I've considered three molecules. So molecule A, it is well inside the liquid. B is within the surface film, and C, which is on the surface. Out of these three molecules, which one has high energy? Hello, are you guys able to hear?
Highest
C,
energy.
sir. C.
So, see, the symbol used for potential energy is U. Can I say potential energy of C is greater than the potential energy of B is greater than the potential energy of A? A has the least. So I need not worry about the molecules which are well defined inside the liquid, which are well below the surface film. So I need to be concerned about the molecules which are within the surface film and the ones which are exactly on the surface. Since they have more energy, what will happen? They tend to what? They tend to be more unstable, right? So, but what we are trying to say, it needs to be stable because no force is acting on it, right? There is nothing sitting on top of it. So for this surface to have minimum energy, what is supposed to happen? For the surface film means this PQRS, this whole thing. For the surface film to have minimum energy, what should happen is the number of molecules that are present within the surface film should be less. Why should it be less? Because more particles are there in that surface film, then all those particles potential energy will get added, as a result of which the surface film will have more amount of potential energy, more unstable. So for that to happen, what will they do is these molecules on the surface will try to occupy minimum area. Okay. Thus, the surface film tends to have minimum surface area. That is what is going to happen because they will try to come below the surface. They will try to come below this line. If that should happen, what property should it possess? It should possess the property of elasticity. That is the reason why this region alone has a property called as surface tension because of its elastic nature. All these things are happening only because of that. Are you able to understand?
Yes, sir.
Yep. Good. So this is the molecular theory of what? Of surface tension. Why exactly surface tension is happening? That is why now you can connect all the dots and read the statement. Now you will try to understand. So it is a property of the liquid by virtue of it, which the free surface of the liquid at rest. So here also I'm using the word rest because there we discussed about stable equilibrium. So behaves like an elastic stretched membrane. Tending to what? Tending to contract so as to occupy minimum surface area. It is all happening. It is trying to occupy minimum surface area due to what reason? Can you fill in that blank? U2 dash. By it maintaining a minimum surface area, what is it able to achieve? Yeah, please. It is trying to decrease something. What is it?
Potential energy.
That's the answer. It is trying to decrease its potential energy. So this property is what is helping for the liquids to have a property called as surface tension. Clear?
Yes, sir.
Yes, sir.
See, one such example is needle supported on water surface, which I showed you. Similarly, so all these are examples which I will try to get some pictures so that you will have a better clarity. Okay. So since we are talking about the potential energy of the surface, we will speak about a special type of energy called as surface energy. Means we will be concerned about what is the energy possessed by the molecules on the surface. That we will see tomorrow. So till here, you revise and come. Maximum 2 more classes will be able to complete this chapter. Okay. So start preparing. Okay. Is there any other doubt from today's class?
No, sir.
So the main aim of surface tension is to reduce the potential energy, sir, at the surface.
Yes. Because see, potential energy of the molecules. See, molecules on the surface. What are we saying? Molecules on the surface and in the surface film. So molecules on the surface and within the surface film have more amount of potential energy. So to decrease that, they will try to occupy minimum area. That is the meaning.
Okay, sir.
Okay. So that is a naturally, see, that's a spontaneous process. You know what is spontaneous? Chemistry, naturally happening process. Because see, I'll ask you, let's go back to the ball example itself. If I leave this ball, what is going to happen?
It will fall down.
It will fall down. Why is it happening?
Due to gravity acting on it.
Okay. So you're looking at the way that gravity is the reason for its pulling. I will give you a different version of it. The other way I'm trying to state is, it is trying to decrease its own energy. Does it make sense? Because it has potential energy associated with it. The ball doesn't want to have its potential energy. So it is releasing its energy in the form of kinetic and trying to reach the minimal potential energy. Right? Both are same only actually. You told gravity is pulling, you spoke about the reason. I'm giving a different version of it. Are you able to understand, Rohan?
Yes, sir. Yes, sir.
Right? So I'm trying to say it's trying to decrease its potential energy. By doing what? In this context, it is trying to do decrease its potential energy by converting it to kinetic energy. Whereas in the case of the surface molecules, they are not moving actually, because they don't have kinetic energy associated. So what will it try to do to decrease its kinetic energy? It will try to occupy
Let's see.
minimum surface area. So it has to do something to release it. That's what is happening here. Clear?
Yes, sir. Clear, sir.
Yeah. Okay. Okay, if there are no more doubts, we can wind up. Just wait for a minute.